So now let's talk about nuclear chemistry. I know that's radioactivity, spontaneous decay of radioactive elements. Whatsoever, go and read your slide. All those notes, know them. I'll be calculation based as far as this video is concerned. Though I will also say few things that may not be necessarily a calculation. So let's just start from here. Calculate the average binding energy per mole. Okay, when we are talking of nuclear chemistry, we are talking of under electricity. For those of us who are doing phase 1 or 2, electron moves, proton does not move. But under nuclear chemistry, we move proton. Am I communicating? Proton moves. Proton. We change the proton of a particular element to another due to radioactive activity. Due to radioactivity, do we grab? You can read all that in your slide. Now, calculate the average binding energy per mole of this. Show the answer in kJ per mole. Then we are given uranium 235 has 92 protons, 143 neutron, and has an observed mass. So now the first thing, you are not getting the binding energy directly. The first thing you find is the mass defect. The mass defect is related to binding energy. Mass defect. Please take note. Your mass defect equals to proton plus neutron minus AMU minus the observed mass. This one for the observed mass. Take it as that. Please, it's not this minus this. In the slide, I saw something like this minus this. It's going to give a negative answer. Even though the end of the answer, they removed the negative. They did not show it. But this one is the biggest. Take note. Please take note. It's this minus this. In case you want to do your exam and you are doing this minus this and you get negative answer and you see the answer in the option, that's very wrong. Please. It's proton plus neutron minus the actual mass of the, are we together? The actual mass of the element. So now, and we are told that one neutron equals to this, one proton equals to this. One proton is this, one neutron is this, one proton is this, and it has 92 protons. So if we want to convert this to U, that means we are going to multiply 92 times this. So the mass defect is going to give us the proton is 92 times 1.007825, 1.007825 plus neutron, it has 143 neutron, 143 times 1.008665 minus the actual mass, the observed mass given to us. Now an observed mass of this 235.04393. So if you multiply these two together, so just to save the time, so I have to pause it and do the calculation. So this times this give us this times this give us this. So if you add them together, you get this. So minus this, you get this. So please take note, the binding energy now, once you have your mass defect, is equivalent to the binding energy by multiplying into the speed of light. Binding energy is equal to your mass defect, change in mc squared. But this guy is in U. You have to convert it to kg. Yeah, and we are told that 1U equals to this times 10 raised by minus 27 kg. So how do we convert this guy? If 1U equals to so kg, then this one will give us our mass defect now will give us 1.915065 times 1.6605655 times 10 raised by minus 27 kg. Please, in nuclear chemistry, but don't approximate to all those 660, write them out, don't approximate. 1U equals to so kg. So this U is greater than 1. To get it in kg, you are going to multiply it by that kg that is equivalent to 1U. So this guy is going to give us 1.6605655 times 10 raised to the power minus 27 multiplied by 1.915065. So this guy is going to give us something like, so our change in mass now equals to 3.1801 0.001 times 10 raised power minus 27 kg. So that's the mass. That's the mass defect. Now our binding energy will give us what? Change in mc square. You don't have to be given c. You know c, speed of light, is constant. So these are change in m, 1801 times 10 raised power minus 27. What's the speed of light? 3 times 10 raised power 8 square. Are we together? So this will give us times 9 times 10 raised to power. So our answer equals to 2.8621 times 10 raised power minus 10 joule. Yeah, that's the answer. That's our mass defect. But we asked to find it in kilojoule per mole. Kilojoule per mole. So if you want to convert this to kilojoule, you multiply by 10 raised power minus 3. So it's going to give us 2.8621 times 10 raised power minus 13 kilojoule. You multiply by 10 raised power minus 3 from joule to kilojoule because we have 1000 joule in 1 kilojoule. Sure you get. So this in kilojoule. But in kilojoule per mole, 1 mole of substance equals to 6.02 times 10 raised power 23 Avogadro's this thing. So is it 23 or minus 23? Okay, it's 23. Now to convert this guy, now 1 mole is equivalent to binding energy. 1 mole of that stuff is equivalent to our binding energy multiplied by 6.02 times 10 raised power 23. So this binding energy multiplied by this, then we get our multiplied by 6.02 times 10 raised to power 23. So our answer is 1.723 times 10 raised to power 14 kilojoule per mole. So that's the final answer. It's not hard. There is nothing. There is just normal addition and subtraction. So any question you see on this, you can actually these are the steps. Converting to kilojoule per mole. These are everything you need. Any question related to this, whether it's uranium or any other element, just understand the basic. Now I move on to okay, sorry. Now they can also ask you to find it in kilojoule per nucleon. This kilojoule per mole, they can ask you to find it in per nucleon. Now binding energy per nucleon. Binding energy per nucleon equals to our binding energy over number of nucleons in the nucleus. Are we together? We want to convert it to, now we've converted it to kilojoule per mole, but kilojoule per nucleon will give you what? Binding energy over number of nucleons in the nucleus. What are nucleons? Nucleons are proton and neutron. Sure you get. So that's that for that. So let's move to nuclear reaction. But before that, let me just make this notice. Binding energy is the definition. I told you go and read it in slide, but for you not to make mistake, binding energy is not about binding things together. If you are being asked to define it, the definition of binding energy is the energy required to separate the nucleons in the nucleus of an atom to their individual how can I put it now? Like in the nucleus you have proton and neutron. The binding energy is the energy required to separate the proton from the neutron, to separate the proton, like to separate them apart completely until they are completely separated. Yeah, when you see something related to that, regardless of how they put the English there, just speak it. It's the energy required to separate the nucleons. In the nucleons, we have the proton and neutron. That is to separate the proton from the neutron or the neutron from the proton whatsoever. So that's the definition of binding energy, not energy to bind something together. For this time, this is the energy to scatter, like to separate two things from each other. Do you understand? So now nuclear reaction. I'm still coming back to this question, so I'm going to discuss it under nuclear reaction. Okay, let me open another page to start nuclear reaction. So now nuclear reaction. Nuclear reaction. So nuclear reaction. We have like four types. We have transmutation, we have fission, we have fusion, and this other one. We will get there. Now let's start from fission and fusion. Now fusion, whenever you see you are binding things together. Whenever you see I, fission, you are splitting. So fusion is just like um um bringing two nuclei, bringing two nuclei of bringing two nuclei together. Small light nuclei, merge them together to give you an heavy nuclei, fusing them together, combining them together. What I need you to know is not even to cram it. Just know that fusion is talking about, and you know what they are. You know those points there. Two light nuclei, you know, merging them together to become an heavy nuclei. While fission is like splitting a heavy nuclei to two or more light nuclei. And don't forget, these two energy will be released. So any option you see that doesn't have energy or Q means quantity of it, don't pick it. If all the option doesn't have, then just pick the one that is correct. But take note of those Q. When fission is taking place of fusion, there's always a release of energy. There's always a release of energy. Any forms of radioactivity, energy will be released. And not just small amount, huge amount of energy. Take note of that. So now let me start some calculation under fusion.